And hey, it's great to see you here. I'm Kaiyu, and I will talk about formal reasoning meets LLMs towards AI for mathematics and verification. Okay, so we are now kind of in an arm race of large language models in which every leading company releases a new model in every few months. So at the center of this arm race is math and coding. For example, when OpenAI introduces O1, you typically see this kind of charts showing that its capability on various benchmarks. And you see the math competition like AIME and the coding competition like Codeforces are usually highlighted. And similarly, when Google released Gemini and when XAI released Grok, they also highlight the capability in math and coding. And in November 2023, XTX Markets, which is a British hedge fund, launched the AIMO prize. That's $10 million for AI that can win a gold medal in IMO. And not long after that, in July 2024, Google DeepMind announced that AlphaProof and AlphaGeometry have achieved the silver medal level. I guess that's the content of the last lecture. And if we want to go beyond high school competition math, we have this Epoch AI. It introduced a benchmark called Frontier Math, which includes research level mathematical questions that's curated by professional mathematicians. And not long after that, OpenAI O3 announced that it can solve more than 20% of that, and which came as a surprise because when Frontier Math benchmark was released, people thought, okay, this is going to be, it's going to take a few years for language models to make real progress. But really, after less than 1 year, we have groundbreaking results from OpenAI. So why are people interested in math and coding? Why are they often highlighted? One reason is that math and coding are proxies for complex reasoning and planning. And reasoning and planning, they're not only important for human intelligence, but they are also one of the major challenges for current large language models. And they can really unlock unlimited applications if you can make language models be able to reason and be able to plan. For example, you can have them do travel planning for you and also have language model agent scheduling calendar invites for you. And the second reason that people are interested in math and coding is they are relatively easy to evaluate. Because for a math problem, you can check if the answer is correct. And for coding, you can run the unit test to see if they can pass all the tests. But if you ask your language model to write like a crime fiction, or you ask it to compose a symphony, it's going to be much, much harder to evaluate. You can argue that like crime fiction also involve reasoning, and composing a symphony definitely needs planning. So they also need reasoning and planning, but they are just not as easy to evaluate. So I put it relatively easy here because that as we will come back, we don't think checking the answers or running the unit test is a perfect evaluation. We're just arguing that it's a reasonable evaluation, and we will revisit this point later in the rest of this lecture. Okay, so we know language models are racing to be good as math and coding. And next, we want to briefly introduce the main techniques behind them. Like, how do we train language models to solve math problems? Here, we focus on math, but the discussion largely also applies to coding as well. And we will see later that math and coding are deeply connected. And state-of-the-art math language models are trained using mainly two techniques. One is supervised fine-tuning, or SFT, and the other is reinforcement learning, or RL. And we're going to present a very high-level view and emphasizing the need for data and for verifiability. Starting with SFT. So in SFT, you have a base model that's a generic language model pre-trained on internet scale datasets. And to learn mathematics, you give it additional data that's focused on mathematics. So you can grab web pages from Math Overflow, or you can have papers from archive. And the result of this fine-tuning is called the base math language model. Well, it has seen a lot of mathematics, but it still hasn't yet learned how to solve problems. So the next step is to give it a lot of problems and with detailed step-by-step solutions for these problems. And optionally, in the solution, you can use external tools. So here the model is trained to produce not only natural language reasoning, but also it can call external tools like Python. So this is an example of a problem it can solve. So the most important thing in this pipeline, as you can see, is data set. You need data set for continued pre-training. That's the web documents collected from web, from the math forums like Stack Overflow. And you also have to annotate a lot of data for further fine-tuning, consisting of problems with step-by-step solutions. And I would say collecting this data set is one of the most expensive part in this pipeline, because it cannot be fully automated. You need human to annotate the data, to clean the data, and to transform the data into the data set that you can use. So what if our data set has only the final answer, but not the intermediate steps? This is a scenario where you don't want humans to annotate data very expensively, but maybe you can more cheaply get the data that has only the final answer. So can we still use this data set to train the model? And the answer is yes. We can use reinforcement learning to train the model to generate solutions with only the problem and the final answer. Here's how it works. So you have the problem, and you give it to the language model. And the model generates a solution that has intermediate steps, and that also has a final solution. And you can check if the final solution is correct by comparing it with the ground truth. So here it's a correct solution. And the model can also generate incorrect solution, and you can check. So the result of this verification can be used as reward signal in reinforcement learning. And you can use algorithms like GRPO to optimize the model to achieve high rewards. Well, you can treat the reward for a correct solution to be 1. And if it's an incorrect solution, the reward is going to be 0. So this approach is very simple approach and a very powerful idea. It's actually, the idea is there for several decades, but it was first shown to work for training reasoning language models by DeepSeek R1. That's fairly recently. And this idea is getting a lot of momentum. Just to see how much momentum it has, just 1 month ago, 2 pioneers in reinforcement learning, Richard Sutton and Andrew Battle, won the ACM Turing Award. So here, in reinforcement learning, the key is really the verifiability. So you have to be able to verify the results. You have to be able to tell if the solution is correct or not. Otherwise, you don't have the reward. So if the solution has a final answer, that's a number. If it has a numerical solution, you can always check by comparing with the ground truth. But what if it's a theorem proving problem? So you are asked to generate a proof, but there's no easy way to tell if the proof is correct or not. Can we still do reinforcement learning? We will revisit this point in the later part of this talk. So here we have covered the main techniques to train language models for math, supervised learning and reinforcement learning. I would say any state-of-the-art math language models is kind of like it's a combination of a very strong base model and these two techniques for post-training, and maybe more importantly, marvelous engineering efforts. So the algorithms are very straightforward. Pretty much every leading industry lab is using the same algorithm. But what really matters is who has the better infrastructure, better engineering, and better data set. So then we will ask, will AI soon solve mathematics since we have this very powerful recipe? And the answer is definitely no. So we have a few gaps. So the first gap is, how do we go from pre-college math to advanced math? Existing successes, as we see, they're mostly limited on pre-college math, like IMO or AME. And if you give language models more advanced mathematical problems, they still struggle. So this quote is from Terry Tao, who is one of the most prominent mathematicians nowadays. And he said he played with OpenAI o1, and he finds they still struggle with the most advanced research mathematical tasks. Well, this is kind of expected because mathematical research is by definition novel. And since it's novel, you don't have a lot of data to train language models. And also, O1's, O3's results on frontier math, as we mentioned before, they are on advanced mathematical problems, but they comes with a few caveats. Well, the first caveat is there are financial ties between Epoch AI and OpenAI that were later disclosed. But I would say more importantly, there's a difference between frontier math and the real mathematical research. The problems in frontier math are designed to have numerical solutions. So they are advanced, they are very advanced math, but they are designed to have a numerical solution. So this is kind of counterintuitive because we know most problems in advanced math, they don't have numerical solutions. But they designed the benchmark in this way in order for the models to be evaluated. And so this is related to the second gap. Current models are very good at guessing the answer, but how do we get it to write proofs? And the recent study has found language models still struggle in writing even very basic proofs. So Putnam is a mathematical competition for undergrads. And people recently tried using OpenAI's reasoning model on Putnam. And here's the results. I'm very unimpressed by ChatGPT in the recent Putnam exam. And it can, most answers are worth 1 or 2 points out of 10 points. So this is checked by human mathematicians. And recently, in another paper, researchers evaluated language models proofs for the USAMO exam, and they showed that all the models scored around 5%, so which is pretty low. And the errors those language models are making can be, they can be pretty easy to spot once you pointed them out. But if it's in a long proof, it's very hard to detect them. So here's an example. We are asking the model to prove a very simple inequality. So if ABC satisfies some condition, and then there should be some, you have some results. And here it's making an error. When it tries to multiply an existing inequality by a positive number, it should preserve the direction of the inequality, but it flipped the direction. So that's a very simple error if you point it out. So we argue that current language models, the current approach for training language models, is not sufficient for solving these problems because it relies heavily on data and on verifiability. And when you work with advanced mathematics, as we said, you don't have enough data. The data is very scarce. And when you work with proofs, you don't have verifiability. And in advanced mathematics, most problems requires proofs. So if language models are not enough, what else do we need? In a recent position paper we released on arXiv, we argue that one important missing point is formal reasoning. Here, formal reasoning means you ground mathematical reasoning in formal systems. And formal systems, they can include like first order logic, higher order logic, dependent type theory, or even computer programs and their semantics. And the role of formal system here is to try to verify the proofs and provide automatic feedback on the proofs. So this is very useful because the feedback it provides can mitigate data scarcity. You can have the model learn from automatic feedback, and you don't need to collect as much human-created data. And second, now you can do verification, which enable you to evaluate the model rigorously. So therefore, we argue that to move forward, we really need to integrate formal reasoning into the current approach. So we're going to very briefly introduce Ling, which is a kind of formal system we focus on in this talk. And it's also used in alpha proof, so I guess people already have some familiarity on Ling. So here is here's a program in Ling. In this program, you first define natural numbers. So a natural number is either 0 or a successor of another natural number. And then you define addition between two natural numbers. So this is just a recursive function. And then you can state and prove some theorems about natural numbers and addition. For example, you can prove a plus b equals to b plus a. And this here is only one file in Ling. And if you are using Ling to write formal mathematics, it's similar to using Python or another programming language to develop software. So you have one file, and this file has the proof, and the proof is, it has semantics. So you are starting, it corresponds to a proof tree. At the root of this tree is the original theorem you want to prove. And every step in this proof decomposes the proof goal into several simpler sub-goals. And you can do that recursively until all the sub-goals are solved. And this is one file. And files are organized into larger units, like a project can have many files. And the project can be open sourced on GitHub. For example, in your project, you can define real numbers. And someone else's project can build on your definitions of real number, and they can formalize, for example, like optimization theory. So this is similar to how you develop software. And one example of using AI with Ling is alpha proof. That's the content of the last lecture. And it's a very successful example, and it uses Ling to generate a lot of theorems and a lot of proofs, and verify those proofs, and do search and reinforcement learning to learn the model. So in the rest of this lecture, we will be talking about mainly two tasks at the center of using Ling and AI. So first is theorem proving. In theorem proving, your input is a theorem statement. And you want the model to generate a proof. Here, both the statement and the proof are written formally in Ling, and the Ling can check if the proof is correct or not. So there's no room for the model to hallucinate. And the other task is autoformalization. In autoformalization, you have the informal mathematics, for example, from a textbook, and you want to use your model to translate it into formal mathematics. So next, we will be first focusing on theorem proving. A very straightforward way to do theorem proving is you just give the model what you want to prove, and you ask the model to generate a step in the proof, or you can ask it to generate the entire proof. And well, because if you can generate the next step, you can kind of using search to chain steps together into a complete proof. So I would say like the central problem here is how do you generate the next step? And a very straightforward solution is, okay, we have human written formal proofs. And we can train a model to do supervised learning on those data so that the model can learn how to generate the next step. And this idea has been actually here for like for a while. And earlier work used classical machine learning algorithms like k-nearest neighborhoods. And around 2019, people have started to use deep neural networks for this task. And even later, people are starting to use large language models. And I would say until the use of large language models, we really see a boost in the performance because the model can acquire a lot of mathematical knowledge during pre-training and use that knowledge in theorem proving. So we will be mainly talking about this paper called Lindojo, which was published in New York 2023. Well, in this paper, we provide open source data sets, tools, and models for theorem proving Ling. And compared to previous approaches, the main difference is first, we are completely open. Previous approaches are private and they don't release the data set and the models. And they were done in private labs. And second, we propose a new model to generate the next step in the proof. So here's an overview. So in Ling, we can extract data from human written Ling code. We extract about 10,000 theorems and proofs. And for each proof, we have the steps in the proof. And we also have the lemmas used in the proof and also the definitions of these lemmas. And after extracting this data set, we use this data set to train a machine learning model. And once the model is trained, the model can interact with Ling to prove new theorem. And so here is the model we introduced for this task. It's called retrieval augmented prover or reprover. The motivation is that when you prove a theorem, you almost never start from scratch. You use existing lemmas. And in order to use existing lemmas, the model have to know what lemmas are there and try to decide whether a lemma is useful. So here, given a proof state, that's the goal you want to prove, and also given a library of lemmas. So we first do retrieval. In this phase, we encode everything into vectors. So the state is now a vector, and each lemma becomes a vector. And we compute the similarity between the state and each lemma, and we use the result to retrieve the top lemmas. And after the lemmas are retrieved, we combine the lemmas with the state and use another language model to generate the next step. So here, the model is very simple, but the really important point is how do you get the data set? And as we said in Lindojo, you can extract the data set from Ling, from Ling projects like MathLib and other Ling projects. So here is a summary of a typical neural theorem prover. So on the left, you see a tree. So that's the tree doing proof search. You have an initial state, and your model can generate multiple potential next steps. And you can run those steps, which gives you the next proof state. And you can do that repeatedly until you find a proof. So for this part, you can use any search algorithm like DFS or Monte Carlo tree search. And the second part is how do you generate the next step? So on the right, you see at each node in this proof search tree, you have the current state. So you give the current state to the language model, and it generates suggestions for you. And here, optionally, the language model can take a formal math library, which is the library of lemmas you can use. And so after the Lindojo work, we've seen a bunch of work trying to improve on that. For example, one thing you could do is what we call expert iteration. So which is, so you have a prover. Even if it's not very good, you can use it to prove some, to attempt to prove some new theorems. And in this process, you will get some new proofs. And once you get the new proofs, you can add them into your training set. So now you have a better training set. And you can use the better training set to train a better prover. and you can iterate. So in this way, we show that if you run for more iteration, the performance usually improves until you hit some saturation point. So we've seen a very simple way to build a theorem proving model. You just extract human written proofs, and you train a language model to generate the next step in the proof. Okay, but we would say it's a great step, but it comes with limitations. So the first limitation is still data, because language models work well only if you have a lot of training data, and the amount of human written proofs on the internet is very limited compared to, say, Python code. And also another limitation is inherent to the task of theorem proving. So if you think about other tasks that AI has been successful, like playing Go. So what's the difference between playing Go and proving a theorem? The main difference is in Go, you have a 19 by 19 board. So the possible action you can take is constrained by the size of the board. It's finite. But in mathematics, arguably, you can, your action space is infinite. So there's infinite number of things you could potentially do when proving a theorem. So since the action space is infinite, it's really hard to cover this entire space if you only learn from human-created data sets. And even if you use reinforcement learning, it's very hard to explore the space efficiently doing reinforcement learning. That's a good question. So in the work we have talked up to now, we are just using supervised learning. So there's no curriculum involved. But if you use reinforcement learning, it's natural to have the model first learn from relatively simple examples and then try to generalize. And if you look at more recent work in using reinforcement learning for theorem proving, one major difficulty is how do you choose examples to present to the model. So you want examples to be not too easy, but also not too hard. Mm-hmm. So how do we solve the limitation regarding the action space? So in a more recent work, we try to take a step in that direction, but we choose a very limited domain as a playground. So we prove inequalities in Math Olympiad. So inequalities in Math Olympiad is like you have a few real numbers like ABC, and they satisfy some precondition, and you want to prove a post-condition like this. And we choose this domain because the proofs in this domain is highly regular. So here is what humans would do. Humans would do typically two things. One is you can apply an existing lemma like AMGM inequality or Cauchy-Schwarz inequality. And the other thing people typically do is to rewrite the current formula into a form so that an existing lemma becomes applicable. But even with these two kind of actions, the action space is still very big. For example, for proving this particular inequality, you can apply AMGM. And AMGM can be applied in more than one way. So you have very big branching factor. And you can also apply other inequality like the T2 inequality. And you can also potentially choose to rewrite the formula into this form. So here, the actions you can take is essentially infinite. So how do we navigate this kind of infinite action space? So one thing we do before trying to solve the problem is, okay, let's try to see how O1 solve this problem. And we give a lot of inequality problems to O1, and we manually check their proofs. So as a result, we find a lot of errors in the O1 produced proofs. And we checked 20 examples. O1 preview proved none of those examples. And the more powerful O3 and also DeepSeek R1 also only proved 3 or 4 out of 20 examples. Whereas a typical gold medalist, like a human gold medalist, can prove at least 15. So then let's come to our method. So as we said, we categorize the steps you can take in this particular problem into two kinds. First, we call it scaling. Scaling is you apply an existing lemma, like Cauchy-Schwarz, to a part of the current formula. So in this example, you find that the left part of the formula can be used for Cauchy-Schwarz, and which gives you the result on the right-hand side. So what's special about scaling is the number of scaling you can do is finite. This is because, okay, you only have a finite number of lemmas, and each lemma can be applied in only a finite number of ways. So it's actually possible to enumerate all the scalings, all the possible scalings in this space. And besides scaling, another category is called rewriting. Rewriting is you are given a formula and you want to transform the current formula into another form. And rewriting is very different from scaling in the sense that the space is infinite. So given any formula, there are infinite number of ways you can rewrite it. So the key insight here is that after we make this categorization, our algorithm can enumerate all the possible scalings using a symbolic algorithm, whereas the rewriting, the infinite space, can be handled by large language models. So we combine the next step generated by the symbolic algorithm with language models, and we use some heuristics to filter the results to reduce the number of goals you have to improve search. And as a result, we solved a much more problems compared to DeepSeek R1 and also O3. So here on the top, you see R1 proved 4 theorems. Humans can prove 15, whereas our system called LIPS can prove 16 theorems. And at the bottom, we evaluate our system with a few benchmarks and compare with existing methods. So here's one example, one interesting example proof discovered by our system. So here it's interesting because it's from Ivan Chen, who is the IMO coach for the Team USA. And he has a problem set, and he said this problem has no hope to be solved by AMGM. But we find that the proof discovered by our system uses only AMGM combined with clever rewriting. So it can actually find proofs that humans do not know how to find. So here's the takeaway. The challenge in theorem proving is how do you efficiently explore a potentially infinite action space? And while this is a very hard problem, but if you are working on a specific domain of mathematics, you can use domain insight to structure the action space so that the action space become more feasible. But it is an open problem of like whether you can generalize this approach to be domain general. So after talking about theorem proving, we will be going to autoformalization, and like feel free to bring it up any questions anytime. So in autoformalization, we have informal math and we have formal math, and we want the model to be able to build a bridge between them, like translating from informal to formal. And here, actually, we have two slightly different sub-problems. First is, how do we autoformalize the theorem statement? And second is, how do we autoformalize the proofs? In statement autoformalization, the model only takes the statement and produce the statement in ling. But in proof autoformalization, the model have the informal statement, the informal proof, and also the formal statement, and it only produces the formal proof. So these two sub-problems have different challenges. Let's talk about statement formalization first. For formalizing the statement, it's really hard to do the evaluation. Because, for example, here the informal statement says there exists an infinite number of primes. And the formal statement says for any natural number n, there exists a p that's greater than or equal to n, p is prime. So this is obviously a correct translation of the informal statement because it implies the infinity. But the problem is it's not the only correct solution. So if if we produce this solution, we change p greater than or equal to n to p strictly greater than n, well, essentially it's the same. And we can even make it more different. We can make n also a prime. And for any human, you can easily see, okay, these three statements, well, they are slightly different, but they are essentially the same thing. But this creates a problem for machine learning. So if the machine learning model produces one of them, how do you know if it's equivalent to the ground truth? You may want to say, okay, can I like check the logical equivalence? But the reality is this kind of checking the equivalence between two theorems is computationally infeasible in general. And in practice, researchers have resorted to heuristics or human evaluation. But if you rely on human evaluation, it's going to be very expensive and not reproducible. And if you resort to proxy metrics or heuristics, it's not going to be accurate. So that's the challenge for evaluating the auto-formalized statement. How about proofs? Proofs, we have another challenge. Human written proofs are, even if they are very rigorous, they are not rigorous enough to be formalized. They often have holes. Like one kind of hole is like mathematicians often say, okay, this case is left to the reader. So if it's left to the reader, your model has no way to figure it out from the text. It has to figure it out by their own. And there are more subtle holes in the proof that we will cover later. But for the model to be able to auto-formalize the proof, it kind of have to fill in all those kind of gaps, which can be very difficult. So we've covered two key challenges in auto-formalization. For statement, we don't have a reliable automatic evaluation. And for proofs, the model have to fill in all the reasoning gaps. And in this project, we want to address both problems. So that sounds very intractable, but a lesson we learned in this project is that since intractable in general can be made tractable if you restrict to a very specific domain. And the domain we choose is Euclidean geometry. Euclidean geometry, it's one of the oldest branches in mathematics, and it has been used to test human intelligence for more than 2,000 years. And recently it has become like interested by the AI community because of the alpha geometry work, where they have an AI that can solve IMO level geometry. So in this work, we show that Euclidean geometry is not only a good domain for theorem proving, it's also a good domain for auto-formalization. And more concretely, we collect a benchmark called Ling Euclid in Euclidean geometry. It consists of 48 problems from Euclid's Elements Book 1 and more than 100 problems from UniGeo, which is an existing data set. So let's look at one example in our data set. So this is directly from Euclid's Elements. It's proposition 1 from book 1. It's basically you have 2 points A and B, and you want to show that it's possible to construct an equilateral triangle. So for each problem, you have the diagram and the informal theorem statement, and also the informal proof. And when constructing the benchmark, we try to manually formalize this problem in Ling. So on the right-hand side is our formalization in Ling. As you can see, it corresponds very closely to the informal version. Like the first step is you draw a circle, BCD, that's centered at A, and B should be on the circle. And the second step is you draw another circle, and you try to find the intersection, and you connect everything, and then that's an equilateral triangle. So there are only 5 or 6 steps in the formal proof, and each step corresponds perfectly to what's being done in the informal proof. And we did this for all the 48 theorems and proofs in Euclid's Elements Book 1. And this is aesthetically very pleasing for me because to the best of our knowledge, we are actually the first to formalize Euclid's Elements in a proof assistance like Ling. And while we want to keep the proofs very faithful, in the sense that there's a direct correspondence between formal and informal. And as we will see later, this is not always trivial. And during this process, we find a few very interesting errors in Euclid's elements. I think we can probably go over one of those errors just to see how formalization can help you check mathematical proofs rigorously and uncover bugs in a proof that you may think it's already very rigorous. So this is proposition 24 from Euclid's book 1. It says if you have two triangles, and then the two triangles have two pairs of edges equal to each other. So AC equals to DF, and AB equals to DE. So blue equals to blue, red equals to red. And the angle A is bigger than angle D. So you want to show that BC is greater than EF. Well, this doesn't look very difficult, and I'm going to show the original proof by Euclid. So first, you try to move the triangle from the left to overlap with the triangle on the right. So C will become G. And then you try to connect F and G. So now the problem becomes proving EF greater than EG. This is easier because EF and EG are now in the same triangle. And according to a previously proved theorem in the same book, in the same triangle, a bigger angle corresponds to a bigger edge. So you only have to prove the relationship between these two angles. You have to prove the big angle here is indeed bigger than the small angle. So how? Just notice that we have an isosceles triangle here. We have DGF. DG equals to DF. And by a previously proved lemma, in an isosceles angle, in an isosceles triangle, you have two angles equal to each other. So then you can argue that the bigger angle is bigger than the DFG because it's a superset of the BFG. And the DFG is equal to DGF. And the DGF is bigger than the smaller angle. Then you have proved the bigger angle is bigger than the smaller angle. Okay, so this is very trivial, but the proof is actually wrong. Anyone knows why? No? Okay. Well, technically, it's not wrong for this diagram, but what if they look like this? So let me try to replay the proof. First, move the triangle to the from the left to the right. Second, connect G and F. Now we want to prove EF greater than EG, and we want to use this isosceles triangles, alpha. So this alpha are equal, and we want to prove X greater than Y using alpha, which does not work directly because in the previous diagram, alpha is a part of X, but now alpha is outside X and Y. So you cannot use it as an angle in the middle anymore. So the original argument breaks in this diagram. So how do we fix this proof? Well, luckily it's fixable. Otherwise, we will probably publish a bigger paper. First notice that the angle DGE, that's alpha plus Y, it's an inner angle in a triangle, so it's smaller than pi. That's trivial. And second, 2 pi minus alpha minus X, that's DFE, is also smaller than pi. If you add these inequalities together, alpha will cancel out, and you get X greater than Y. So it can be fixed, but as you see, this proof is quite different from Euclid's proof. So that's why we think Euclid has made an error here. Or technically, it's not an error. It's like this proof has two cases. These two cases are slightly different. And one case is more challenging than the other. But Euclid omitted the more challenging case and focused on the easy case. Okay, maybe that's a very interesting digression that's not related to AI, but it showed how AI and Ling can make things more rigorous. So let's go back to AI. So in our benchmark, the first thing good about it is it enables you to check whether the auto-formalized theorem statement is correct. So here's how we check if the statement is correct. We have a ground truth, and we want to check if the model-generated statement is logically equivalent to the ground truth. So given two theorems, T1 and T2, we check it by proving T1 implies T2, and T2 also implies T1. And here we use an automated reasoning tool called SMT solver. But if you remember, I said this is infeasible, but how it becomes feasible now. And it turns out now it's feasible because the theorems in Euclidean geometry takes a particular form. They are not general theorems. So problems intractable in general can be made tractable in a specific domain. And so that's how we check the theorem statement. Another problem is auto-formalizing the proofs. So here in Euclidean geometry, we want to show that there is a well-known kind of gaps in the proofs. We call diagrammatical reasoning gaps. I'm going to show that using an example. So proposition 1 from Euclid's Elements book 1. Given 2 points, A and B, you can construct a equilateral triangle. Here is Euclid's proof. Draw a circle centered at A, and B is on the circle. Draw another circle centered at B, A is on the circle. Take their intersection, C, and connect everything. You get an equilateral triangle. Anyone disagree with this proof? No? Okay. The problem is, did we prove C actually exists? Did we prove these two circles actually have an intersection? We didn't. And actually, if you try to prove it, so this is proposition 1. So to prove this proposition, you can only use the axioms. There's no existing lemmas. And if you try to use Euclid's axioms to try to prove these two circles intersect, you cannot prove it, actually. So it's not provable. But no one bothers to prove it because it's just so obvious in the diagram. But it becomes a problem if I want to translate this proof in Ling. When I formalize the proof in Ling, Ling does not know what is the diagram or what is obvious in the diagram. So I kind of have to formalize what is obvious in the diagram. I believe this. I was in the Zoom in the last lecture. I believe someone asked a question about how do we formalize Euclidean geometry in Ling. I think this is very closely related to that question. To formalize Euclidean geometry in Ling, the most important thing, or one of the most important thing, is how do you formalize the concept of being obvious in the diagram. And luckily, this problem has actually been solved before. So this is a work from Abigad, who is a professor in philosophy, now in CMU. So Abigad essentially identified a set of axioms that's not in Euclid's axiom system. You can think of it as like an unspoken axiom or hidden axiom. And so what is being obvious in the diagram, it is just if a fact is a consequence of those axioms, then it's obvious in the diagram. So now we have a computational meaning of obviousness in the diagram, and we can implement an automated reasoning algorithm to try to derive things that are obvious. So let me put everything together. So in this work, we have a benchmark. So in the benchmark, we have a diagram, we have informal math, and we have a ground truth formal statement that's written by human. So now we use a model to do auto-formalization. It generates a formal theorem, and we can check whether it's equivalent to the ground truth using SMT solvers to prove that they imply each other. So after checking the statement equivalence, the model can also do proof auto-formalization. Say it generates this proof, and we give this proof to Ling. Ling will identify a set of holes in the proof. And we give those holes to SMT solver which will tell us if the holes are obvious in the diagram. And if everything works, then we conclude, okay, this is a correct formalization. So what our benchmark really do here is we provide like a protocol that you can use to rigorously evaluate autoformalization. And so after collecting this benchmark, we also did some very simple experiments using just GPT-4 and the GPT-4 vision. And here we don't train the model, we just give a few demonstrations to the model and ask it to auto-formalize the theorem statement. So blue here is GPT-4 and green is GPT-4v, which also takes the diagram as input. And so here are two takeaways. One is if you look at the x-axis, is how many demonstrations you give to the model. So if you give the model more demonstration, it's going to do better. But even if you give 5 demonstrations or even more, the model get only about 20%, which is pretty low, which shows autoformalization is very challenging. And if you compare green with blue, you see green is a little bit better, which shows if you give the diagram to the model, it has a stronger understanding of the geometry problem. And here are some takeaways. We identified 2 challenges in autoformalization. For theorem statement, you don't know how to evaluate. For the proofs, there are too many holes in the human written proofs. And we address them by limiting to a specific domain. So in this domain, we can build an equivalence checker for the statement. And we can build a tool that can fill in all the gaps. But still, the open problem is really how do you generalize across a broader set of mathematical domains. So now we've covered both tasks, autoformalization and theorem proving. And this is the end of this lecture, and I'm happy to take questions.